Hi everyone. Today we'll take a look at quadratic functions. So I'd also like to mention before starting this video, we'll also take a look at polynomial functions to a higher degrees as well. So we'll start with quadratic, move to cubic, and then move to higher degree functions. So you can expect at least 2 videos, if not 3 videos, where I explain quadratic, cubic, and polynomials. So I'll explain all of their properties, how they look when you graph them, and we'll do some questions with them as well. All right, so let's get started with quadratic equations. So quadratic equations or quadratic functions are probably the most simplest polynomial function, right? I mean, you have your linear functions, but that's pretty basic. So we're going to take it a step. So we're going to increase it up a step. All right, so we have the general equation, right? So the general equation, right? That's the first thing I'm going to discuss. So we have the general equation. So the general equation goes like this: ax squared plus bx plus c is equal to 0, where a cannot be 0, okay? Because if a is 0, then this part is, this part doesn't exist, right? Then this part doesn't exist, and we just have bx plus c, which gives it a linear function or linear equation, right? So that is the condition for quadratic function, right? And we have the general equation right here. Okay, so one more small note that I want to make is, note, quadratic equations always have 2 roots, right? Quadratic equations or functions, right? Functions always have 2 roots. Have 2 roots. Okay, this is key. Okay, so these 2 roots can either be imaginary or both can be real. Because remember, imaginary roots always come in pairs. Remember, we talked about complex numbers, right? When we have something like this. So if we have if we have a complex number, z is equal to a plus ib, its conjugate will also be a root, which is z is equal to a minus ib. So either, if one root's a complex number, the other will also be a complex number. Okay, so that's one more thing. So now let's look at a very quick example. A very simple one, nothing too crazy. So we have a simple quadratic equation, which is x squared minus 5x plus 6 is equal to 0. So we can solve this multiple ways, right? You could use a quadratic formula completing the square, but I'll go with factoring because it's the most easiest simple approach, right? X minus 2 times x minus 3 is equal to 0. Hence we have x is equal to 2 and x is equal to 3. These are our 2 roots, right? Very simple, nothing too crazy. All right, so now one more thing that I quickly want to go over is the quadratic equation. So let me change the color again. So we have roots of quadratic equation. Right here. Okay, so the roots of a quadratic equation. The roots of a quadratic equation and I'm going to write the general form again, right? Ax squared plus bx plus c, right? I'm going to keep it in parentheses, is given by right here. So we have x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. Okay, and right here. Okay, so one more thing that I want to explicitly mention here, right? This part that I'm going to highlight in green right now. B squared minus 4ac is called a discriminant. Okay, and it's going to have a lot of use later on, right? Because I'm just going to say discriminant, and you should know what I'm talking about. If I say discriminant, we're going to find the discriminant here. You should know. Okay, we're finding b squared minus 4ac. Right? It's very important and to solve questions, right? Because what's going to happen is sometimes they're going to give you a certain function, and they're going to ask you, show that this function is always positive, or it's always negative, and that's where discriminant is going to come handy. It can even come really handy in certain other application questions as well. So it has a lot of direct and indirect use as well. So I'll just quickly change the color again. I'll keep it right here, and I'll say D stands for discriminant, right? Discriminant, right? And it's D is equal to B squared minus 4AC, okay? That's what it is. So discriminant is B squared minus 4AC. All right, so now let's look at, just another quick thing. So the new thing that I want to mention is equations convertible to quadratic form. So oftentimes we're not directly given a quadratic equation. Maybe we're given equation raised with a power to 4, right? So let's take an example again. So equations convertible to quadratic form. So if we have, an example like, x to the power 4 minus 5x squared plus 6 equals to 0. So the way we can solve this question is, right, we can solve this question by making a very simple substitution. And that substitution is going to be like this, right? We're going to let t is equal to x squared. So now what we do is wherever we see x squared, we replace it with t. So we have x to the power 4, or we can also write this as x squared whole squared, right? So we basically have t squared minus 5t plus 6 is equal to 0, right? So we can factorize again. T minus 3 and t minus 2 is equal to 0. T is equal to 3. T is equal to 2. Like this. So now we're not done yet, right? Because we have our values in terms of t. We need x, right? So we know x is equal to plus or minus the square root of t, right? So we have x is equal to plus or minus the square root of 3 and plus or minus the square root of 2, like this. So these are our final answers. Because it was raised to the power 4, we actually have 4 answers, right? Plus square root of 3, minus square root of 3, plus square root of 2, and minus square root of 2. So here I just showed you, a simple way how, we can use the quadratic equation or the quadratic function to solve slightly complex questions. Let's look at one more different variation of this. So I'm going to change the color again, make it purple, and let's look at another example. So we have, in this example, it's going to be slightly different, right? We're going to have, basically we have to find the roots of the equation again, right? Basically we have to find values of x which satisfy the equation. So we have 4 raised to the power x minus 3 times 2 raised to the power x plus 3. And then we have plus 128 is equal to 0. We have to find x, right? So what we do is we slightly, rearrange what we have, okay? So what we're going to do is I see 2 raised to the power x here, right? So I'm going to break this up first. So I'm going to write this as 2 raised to the power x, like whole squared, like this, okay? Then I'm going to break this up. So 3 times 2 raised to the power x times 2 raised to the power 3, right? We can break this up. Simple exponent rules, right, is equal to 0. Now I know this is 8, right? So I can multiply this and this together. So 8 times 3 is 24. So I'll rewrite the same thing again. 2x whole squared minus 24 times 2 raised to the power x plus 128 is equal to 0. Now I'm going to make a substitution. So the substitution will be let t be 2 raised to the power x. So everywhere there's 2 raised to the power x, I'm going to put t there. So I'm going to put a t here. I'm going to put a t here, right? So what I'm going to have is t squared minus 24t plus 128 is equal to 0. Now I have a quadratic function, right, or a quadratic equation. I can use, any method, right? But I can see factors here. I can see 16 and 8 because 16 times 8 is 128 and minus 16 minus 8 is 24. So I'm gonna go ahead directly make the necessary necessary factorization, right? So I'm gonna do t minus 16 here, and then I'm gonna do t minus 8 here as equal to 0. So I have t is equal to 16 and 8, but we're not done yet, right? Because we have in terms of t, we want x. So I'll bring it back to purple, right? So I know 2 raised to the power x is equal to 16 and 2 raised to the power x is equal to 8, right? I know 2 raised to the power 4 is equal to 16, so I'm going to go ahead directly here. Or if you don't, you can use log base 2 to 16 is 4, right? You can put it in your calculator and check that. And here x is 3. So these are our two answers, okay? So now let's look at one more quick example. This is kind of out of the box, okay? All right, so I have to find the roots of this given equation right here, right? I have to find the roots of this equation right here. So, I would suggest that you pause the video and give it a go. All right, so let me change the color, right? So I'll take yellow. I'll take lime, right? So I have x minus 1 times x minus 2 times x minus 3 times x minus 4 is equal to 0. Sorry, not 0, it's equal to 3, right? So now, just before I start, if you have just done x minus 1 is equal to 3, x minus 2 is equal to 3, x minus 3 is equal to 3, x minus 4 is equal to 3, and then, found different values of x, that's wrong, right? That will not work. Okay, so this is definitely an out-of-the-box question, and I'm going to make, certain, adjustments here. So what I'm going to do is I'm going to multiply this and this together, okay? Let me erase this. Let me use a different color, okay? So I'm going to multiply x minus 1 and x minus 4 together. And the reason I'm doing that is because I see something common which I can work with them. And the thing is, just a second. So when I do this, right, I'm going to get x squared plus 4 minus 5x, okay? When I expand these two together, okay? When I do that. When I do x minus 2 and x minus 3, I'm going to get x squared minus 5x plus 6. So I'm going to get x squared minus 5x, right? I'm getting x squared minus 5x common in both terms. It's just the final constant value, which is different. So I can do something with it, right? So that's what I'm going to do. I'm going to work with that. So first I'm going to take x minus 1 and x minus 4, okay? So when I do that, I have x minus 1, or you know what? Let me just expand it right off the bat. There's no need for me to, break another step. So I have x squared minus 5x plus 4, like this. Okay, let me change the color again. Let me take purple, like here. Now I'm going to have x squared minus 5x plus 6. Now, which is equal to 3, right? Which is equal to 3. Okay, now I'm going to make a substitution here. Okay, the substitution I'm going to make a very careful substitution here. I'm going to let t equal to x squared minus 5x plus 4. So what am I going to do with this, right? Because I don't have x squared minus 5x plus 4. But if you look at this closely, what this is, it's actually x squared minus 5x plus 4 plus 2, right? That's all that is, right? There's nothing, that's all there is, to it. There's nothing else. So when I do that, right, I'm going to have t here, and I'm going to have t plus 2 is equal to 3. Okay, that's what I have. My very condensed equation, right? That's what I have. So when I expand this, I have t squared plus 2t minus 3 is equal to 0. Okay, now I can make simple factors. I know right here I can see two factors. So t plus 3 and t minus 1 is equal to 0, right? So I get two values of t, which is minus 3 and 1, right? Simple. But again, we're not done. We have values of t. We don't have values of x yet. Okay, so now let's substitute the different values of t one by one. So I'm going to break the cases again. So I'll take light blue for the first case. So I'm going to have case 1 right here. So I'm going to have case 1, okay, which is x squared minus 5x plus 4 is equal to minus 3, okay? And the other case is case 2, right? case 2. X squared minus 5x plus 4 is equal to 1. Okay? So when I simplify this, I'm going to have x squared minus 5x plus 7 is equal to 0. Okay? The other case, I'm going to have x squared minus 5x minus 3 is equal to 0. Oh, sorry, my bad. Plus 3. Okay? That's what I'm going to have. So now these are the two equations, right? Now, what I'm going to do is I'm going to have to solve them, right? And I don't see any immediate factors, so I'm going to have to use the quadratic formula. So when I use my quadratic formula, I have x is equal to plus 5 times 25 minus 28, right? All upon 2. Here I'm going to have x is equal to 5 again, plus or minus the square root. 25 minus 4 times a, which is 4 times 1 times 3, which is 12 all upon 2. Okay, so now I'm going to stop right here. 25 minus 28 is a negative number, and square root of negative number gives me complex numbers. Now, remember what the question asked me. It said it wanted real roots, right? So that means the discriminant, right? The discriminant, which I mentioned here, must be positive. Okay, that's what real roots mean. So I'm going to make a note here as well. D should be greater than 0 or greater than equal to 0 for real roots to occur. Okay, so now this, no real roots are here, so I'm going to ignore it. No real roots. Right now, when I break this up, I'm going to have x is equal to 5 plus square root of 13 by 2, and x is 5 minus square root of 13 by 2. Whether it's a positive root or a negative doesn't matter. But I can stop right here, right? I've got 2 roots. Okay? That's how it works. Now, you guys might be wondering, well, should I, put in one also, should I use the other equation in purple? X squared minus 5x plus 6. No, you don't need to. You don't need to, because at the end of the day, values of x are going to come as the same. Okay? So you don't need to. Technically, we do have 4 roots. Okay, if you think about it, we do have 4 roots right here. So we have 2 roots here, but they're imaginary roots, right? Imaginary roots, and here we have real roots. So it doesn't matter. Okay, technically, so we do have 4 roots, which satisfies the condition because the maximum value, power of x that we can have is 4, right? Therefore, the maximum number of roots that can occur are 4, right? Whether they're real or imaginary, we don't know until we solve them. Okay, so now let's look at a relation between roots and coefficients. Again, these are all theoretical part, right? I still haven't gotten to the proper application yet. So let's just look at a little bit more theoretical information. So now let's look at a case right here. So we have if alpha and beta, right? Alpha and beta, right? 2 Greek letters. I'm going to assume them to be the roots of, if alpha and beta are the roots, are the roots of the quadratic equation, quadratic equation right here. So quadratic equation, and we have our standard quadratic equation in the form ax squared plus bx plus c. Okay, so that's what we have. So if you have a quadratic equation in this form, okay, so now let's set them up to equal to each other. So we're gonna have ax squared plus bx plus c is equal to 0. So right, but instead of 0, I'm going to write it in another form, right? It's also equal to, I can write it in this form as well, right? X minus alpha times x minus beta. These are 2 roots. When I do x minus the 2 roots, and I can put a constant forward, right? Because I'm going to have x squared as the first term, and I'm going to have ax squared, right? Okay, so those of you who still don't get this stuff, I can expand it really quickly. So I'm going to have ax squared minus beta x minus alpha x, right? Plus alpha beta. Okay, that's what I'm gonna have. And then when I expand it, I have something in a similar form. Okay, so let's get back to the original derivation. So we have something like this right here. Now I'm going to divide this side by a and this side by a. Okay, so when I do that, I have x squared plus b by a into x plus c by a, okay, is equal to x squared, right, minus beta x minus alpha x plus alpha beta. Okay, so I divided this side by a and I opened the parentheses. Okay, so I've done two things here. Okay, so now I'm going to club these two right here because they both have x, they have the same like terms, right? The coefficients are different, that's okay. So again, I'm going to write the same thing down here because that's all I can simplify down to, right? Plus c plus a is equal to x squared minus, okay, minus alpha plus beta x plus alpha beta. Okay, I have something like this. Now, if you look at this closely, okay, so I have x, right? Then I have b by a, and I have minus alpha plus beta, right? And then I have one more, right? One more. So I have, to get another color, so let's say purple again. I have c by a and alpha beta. So now what I can kind of, say is I've developed, some sort of a relationship between the roots and the constants that exist. Okay, so what I can basically say is that alpha plus beta, right, the sum of my roots, right, the sum of my roots alpha plus beta is equal to minus b by a, right? Basically I have b by a is equal to minus alpha plus beta. I just took the minus sign to the other, the negative sign to the other side, and I put minus b by a, right? That's all I've done. So that's one relation that I've gotten, right? Minus b by a, right? Sorry, I just can't seem to get my handwriting correct today. Okay, minus b by a. And if you look at this, c by a, right, is equal to alpha beta. So the product of the two roots gives me c by a, which is this one right here. But remember, this only works in the standard form when the coefficient of x is 1. Okay, you have to make sure to get the coefficient of x to be 1. Only then will this entire standard result work every time. Okay, so now let's look at one more small thing. So maybe we can look at alpha minus beta, right? So alpha minus beta, I'll just give the result immediately to you first, and then I'll show how I got it. So it's minus square root of d, and this d is not some random variable. It's the discriminant. It's a square root the discriminant upon a, modulus of a. Or if you want, I can write it like this: square root of b squared minus 4ac upon a, like this. Okay, and how we get it is basically if I do, okay, so if I do alpha minus beta whole square, right, alpha minus beta whole square. Okay, if I do alpha minus beta, what do I get? I can rewrite this as actually alpha plus beta whole squared minus 4 alpha beta. Okay, and if you want, I can erase it and I can do it again for you. So if basically what happens is alpha squared plus beta squared minus 2 alpha beta, right? Now, if I add 2 alpha beta and subtract 2 alpha beta, okay, I've done that right here. I've added this. It's unnecessary, manipulation I'm doing right here. So now I have alpha squared plus 2 alpha beta plus beta squared minus 4 alpha beta. Now I can factorize this again, and what I'll get is alpha plus beta whole squared minus 4 alpha beta. Okay, that's exactly what I just did here, right? So let me just rewrite this again. So alpha plus beta whole squared minus 4 alpha beta. So alpha plus beta whole squared minus 4 alpha beta. Okay? Now, I can, make some certain substitutions here because I know this is the sum, right? And I know the sum is minus b by 2a whole squared minus 4 times c by a, which is the product, right? Alpha beta. And this is what did I say it was? Alpha minus beta whole squared, right? Now again, simplify this a bit more. I get b squared minus 4a squared minus 4c by a. Okay? Now if I multiply by a on both sides, or no, sorry, the numerator and denominator by a, right? I have b squared minus 4ac upon 4a squared, right? Again, if I simplify this a bit more, or if I don't even need to simplify this more, I can just stop right here for a second and basically again, point out one small thing, right? B squared minus 4ac is my determinant. Sorry, not my determinant, my discriminant, right? And I have 4a squared alpha minus beta whole square, right? Like this. Now, if I take the square root of both sides, I have square root of my discriminant upon 2a, right? Like, oh, sorry, I made a small error here in the entire thing, actually. So it's actually minus b by a, minus b by a. So this is a squared, a, and like this, right? So now I have square root of d by a right here. And actually the square root of something that's squared is actually not just alpha minus beta, it's actually modulus of alpha minus beta. So this answer will come out as positive, but you know that you can tell by the different variations whether it'll be positive or negative. So this is how we got this result, right? So I'll just make a small box and isolating the working like this, right? So again, I'll just make a star here so you know this is important and you can keep it in mind. All right, so let's look at some theory of equations and the relation between roots and coefficients. So I'll just summarize what we just did in quadratic equations, right? So for quadratic, we had alpha plus beta, which are the two roots, is equal to minus b by a. And we had alpha beta, which is equal to c by a, right? For the equation ax squared plus bx plus c is equal to 0. Now, I said before that, the coefficient has to be 1, right? But it's not necessarily. I just said that. What I meant by keeping the coefficient 1 for x squared is when we were deriving the whole situation. But even if we have our quadratic function as in the form of ax squared plus bx plus c, we can still determine, the nature of the roots, right? Basically, the sum and the product of the roots. So now let's look at cubic equations. So cubic is nothing but an extension of our quadratic equations only. So we have our general term, for ax squared plus, this time we'd have ax cubed. That's a cubic equation. So ax cubed plus bx squared plus cx plus d is equal to 0, right? This time it has 3 roots. So it has 3 roots, and we can name them as alpha, beta, and gamma. Okay, so we have 3 roots. Now, I'm just going to go directly to the relation, and I'm not going to waste my time deriving it, right? If you want, you can see the textbook. The textbook will have some, some sort of a derivation, but you just need to know the final product, which is the sum of the roots. So we have alpha plus beta plus gamma is equal to minus b by a, okay? This is the first result, right? So result 1, just the sum, right? Again, sum. Then we have sum and product. Okay, so this is something like alpha plus beta plus gamma plus alpha plus gamma is equal to c by a. Okay, so now we're actually just multiplying 2 roots at a time here. Okay, this was just 1 root at a time. Technically, if you're going to think about it, this is 2 roots at a time. So it gives us c by a. And then we have our final thing. Okay, so we have alpha, beta, and gamma, all 3 roots being multiplied at the same time, which gives us minus d by a. And IB will probably generally ask you to cubic, right? They won't go beyond cubic. I don't think, I don't recall doing any question where I needed to know the properties of to the power 4 or to the power 5. But you know what? I will be explaining, equations of degree n right now as well. So just in case if it, does come out of the blue, so you're not confused, or you don't, it's not, you should never be in a situation where you don't know it, right? So if I have, an equation of degree n, okay, so this was number 2, so this will actually be number 3, my bad. So number 3 right here. So equation of degree n, right? We don't know. So basically, if we have if alpha 1, alpha 2, alpha 3, all the way up to alpha n are the roots of a a polynomial, right? Are the roots, right? If they're the roots of the function, maybe we have something like f of x is equal to of f of x is equal to a naught x to the power n plus a1 x to the power n minus 1, and so on and so forth till an is equal to 0, right? Something, a general form of this. So basically we have n number of roots, right? Because it's n number of power. So the general, final result, right, which comes is if we have the sum of individual roots, right? So if we have, if you do alpha 1 plus alpha 2 plus alpha 3, all the way up to alpha n, right? So alpha 1 is basically minus a1 by a naught, okay? If we have sum of two products happening, right? So if we have alpha 1, alpha 2, we have plus a2 by a naught, okay? And if we have sum of three roots, right? Alpha 1, alpha 2, alpha 3, all the way, basically alpha 1, alpha 2, alpha 3, basically you're multiplying three roots at a time, right? And taking the sum of them. So we have minus a3 by a naught, okay? And one more final one is basically the products, right? So I'm just gonna do a dot dot. Basically, we have three roots being multiplied, then we have four roots being multiplied, and we have all n roots being multiplied at the same time. So here we have basically have the product itself. So alpha 1, alpha 2, alpha 3, all the way up to alpha n, okay, which is basically minus 1 raised to the power n times an upon a naught. Okay, so basically whether you put a minus sign or not, it all depends upon what degree it is. Okay, so if it's a quadratic where the degree is just 2, right? Basically we have ax squared plus bx plus c, so n is equal to 2. So in that case the product is minus 1 whole squared, right? So which is actually a plus, right? That is why we have a positive sign when we do alpha times beta, which I showed you in the previous example, right? So these are the few properties that you should be aware of moving forward. All right, and this part, basically we'll wrap the video up at this point. Next video we'll take a look at a few more aspects of quadratic functions, and we'll also look at graphing quadratic functions and understanding the nature of the roots and how the parabolas and how the polynomials look when you graph them. All right, so this was all for today's video, and I'll see you in the next one. Bye bye.